I will talk about biological inspiration or biomimicry if you want, and local material, local feedstock for 4D printing composite material. So I am Professor Antoine Le Duigou, and I come from Lorient, which is on the west part of France. So it is the blue spot on your slide here. And I'm supervising the bionics group from now many years. So first of all, I will talk about what I'm doing as supervising and what also my students are doing. Next, I will talk about the context about the presentation, which will deal about marine application and space application or 4D printing material based on, let's say, local and natural feedstock. So two kinds of projects will be described. First of all, the more free project, and then the solar tracker project. So let's talk about the bionics group. So bionics group, just to cut a long story short, the acronym is for biomimicry for innovative composite material. So my background is material scientist on composite material, and then getting interest in the natural strategy to propose, let's say, original multifunctionality. So our purpose is, let's say, to propose material concept or new solution to reduce our environmental footprint. So if we just think about the life cycle of material, first of all, we need to think about the feedstock, local feedstock, and then talking about the functionality during the use phase. Here, the purpose is to develop new generation of autonomous weather-responsive material, thanks to the change of humidity or temperature and so on. But allow changing, but allow also changing by keeping mechanical properties. So let's say enabling paradoxal properties, stiffness and compliance together. Here my main approach is based on multidisciplinary approach, mixing eco-design, so meaning evaluation of environmental impact through life cycle assessment, for example, biomimicry, digital fabrication, 3D and 4D printing of composite, high-performance composite material, natural feedstock and morphological function, and last, the polymer and composite material science. We have organized 3 events the last years, and the last one was dedicated to French-Japanese dialogue between additive manufacturing. So next one, I don't know, but perhaps it would be between French and Australian. So I will see next time. Now let's talk about the context about how the work is done in my group. So first of all, let's talk about the environmental, societal, and economical context. So first of all, we try to go beyond the current design to trigger reduce environmental footprint. So we know that the human have a huge impact on the human on the planet, on the Earth, of course. So we have to change our way of doing material by changing feedstock with renewable material, or let's say at least natural and local one. We need to improve the frugality by just using the right amount of material, and we need to also work about performance. So all these points should be applied also for application on the Earth, but also for out of Earth application. For example, when the European Space Agency, also the NASA or JAXA, think about what will happen on the moon in 10 or 20 years, they think about one thing: how to build something with in situ resource utilization. So this is the main point. So we have common point between development on the Earth and development on the moon. I don't say that we should destroy the moon, of course. Here, for the performance, I focus about the composite material. Composite material, if you have a look at the picture on the right, most of time, basically, let's say the main purpose of composite material is to take benefit about the anisotropy, but this is not the main point currently. currently, many designers are applying, let's say, black metal paradigm, which is just focused on in-plane random properties, which is not very relevant, let's say, solution. So here we just want to focus also on the anisotropy. We also would like to increase the multifunctionality, just not only to focus on the mechanical properties, but on the possibility to have material with high performance, mechanical performance, but also the possibility of sensing or actuating, but also frugality. So meaning the function, the working principle without external source of energy. So here, autonomous actuation. So maintenance, of course. So this is, let's say, one main point of 4D printing, but also end of life with at least recycling, but also potential, let's say, control degradation. And we will talk about that when I will talk about the project. So the main question is how nature inspired our research and how we can develop new concept of, let's say, material with low environmental footprint. So first of all, we talk about, or let's say our research guidelines is following biomimicry, description of, let's say, local feedstock, but also fabrication with 4D printing. The example of all these research guidelines will be applied with these projects among several projects we are driving now. So first of all, let's talk about the Morph project. That's quite nice because I have seen that other researchers on this 4D printing society are also interested in artificial reef. So I am not alone and we are not alone. So that's a good point. So let's talk about what is artificial reef. So if we look at some history point, one of the first one was Japanese that made this artificial reef from many centuries ago. And the main purpose was for fishery or protect human. And this is not exactly the same purpose as what we can find in Europe. For example, in Europe, this is mainly to protect the sea life and to make revitalization of the coastline. I would be very curious to know what is defined as artificial reef in Australia, for example. I know that in US the definition is quite different because in this place we can use many kind of material for that. So if we talk about the material, for example, in the middle, concrete is the main used material. Okay, so you can see the amount of material in Japan that is giant. In France, it's very lower. But what is the solution to do this artificial reef? Is it good to think about? Okay. Is it good to think tire like this or to think brick like this? To be honest, I wish to be, or we wish to be, let's say, more smart or smarter than that, just not to think anything that could be a waste, but to think in a new way of artificial reef by developing concept of, let's say, shape-changing material based on also local feedstock, meaning valorizing local feedstock that allows also the revitalization function with a controlled lifetime. So someone talked about that yesterday, but the selection of the local feedstock or the local material is very important to, let's say, design the durability also. So here, the local feedstock, as we can say, even if there is no, let's say, official definition, let's talk about biocomposite. So this is a blend of plant fiber, but the plant fiber can come from terrestrial locations. So here, this is natural fiber on flax, hemp, cocoa fiber, and so on. But they can also come from seaweed or, let's say, plant fiber from marine area also, and there is a lot of local feedstock, for example. And they can be blended with biopolymer to allow, let's say, at least recyclability, depending on the function we want to trigger, but also degradation on biological degradation. And this is a big issue because what is the biological degradation? and what is the difference with the compostability. So I won't have the time to discuss about that, but this is a main point when we select the material. My work is to define the relationship between the architecture of this feedstock and their function, depending on their role in the nature. So, for example, if you take natural fiber from bast fiber from plant, this is different from a fruit and so on. So that will allow to get different function. Then we need to have better information about what would be the key of their morphing feature, or their morphing potential. So, for example, in plant fiber, this is the moisture sensitivity or the temperature sensitivity. So this, just to make an echo with the last presentation. So in the natural fiber society, this was a big drawback, and this is still a big drawback. So a lot of people say that they want to chemically treat the fiber because they don't want to have this kind of moisture sensitivity. So here, this is exactly the contrary. So we take what is naturally given by the composition. So here we just evidence that we have a huge expansion of the natural fiber. And then we have, let's say, a specific point, which is the leaching. So, for example, if you sink a natural fiber composite within water, you will obtain this, so the browning effect in water. So this is what we observe in scanning electron microscopy. So this is a leaching of material, which is polysaccharide. So this is kind of sugar, if you want, that will be degraded and that will be in the water. So this is the starting point to give functionality to our morphing reef. So if we apply a top-down approach of biomimicry, so first of all, let's find the bottleneck of biocomposite. So humidity is quite a big bottleneck. If we just applied, and this is quite now well known from the community, let's say application from what biological structure can take advantages of humidity. So this is natural actuator that take benefit of the humidity change, or also the architecture, the asymmetric architecture of the structure. So here, by abstraction, we just propose to make the biocomposite in a different way that allows the biocomposite to be sensitive to moisture variation and to trigger, let's say, complex actuation here. So this is a smart material that could be said to be fiber-dominated shape-changing material. So this is quite contrary to what is used as a lot of polymer, as we can see in the literature. So this is a novel function as hygromorph. So what we have done now by applying biomimicry is just to wonder how we can go, let's say, further than just a simple bilayer. So, for example, a pine cone scale here, this is not a bilayer. If you see the distribution, or let's say the material in the cross section, we see that we have a distribution of thickness. You can see also in the plane here on the right that we have a distribution of material that allow a distribution of stiffness. So here, all the distribution of material or geometry allow to have a sequential motion of the pine cone, and not only just one curvature, but several curvatures. So here, just by looking more deeply on the natural product, we can apply this to, let's say, propose spatio-temporal programmation or programming of our hygromorph composite. So if we just work on the shape changing, so again, the biological structure and the distribution of stiffness give us the first idea. Then applying, let's say, very simple Timoshenko equation, where the N ratio describe the ratio of stiffness. So here we can, let's say, describe the effect of the distribution of in-plane stiffness by proposing discretization of the shape changing also here. Going, let's say, above just rectilinear distribution of fiber, we can go to, let's say, curvilinear distribution, and also going more complex monocurvature. And here we have possibility to go to dual curvature and sequential morphing also. We are also to programming of the reactivity. So here, one of the main drawbacks of the composite is about porosity. But if we look on the nature, there is no porosity in the sense of defect. This is channel that have function. So this is porosity that have function, if you want. So here we just look at this point and flow, or let's say a diffusion model, like a peak model and so on, and then propose 3D printed model that is based not on the defect of the 8 layer, but with design, tailored design of channel. So here we are studying the channel effect, the size, the amount, the distribution, and so on. That will have an effect on the moisture uptake, but also on the expansion. And then by applying a distribution of this channel, we have the possibility to control the kinetic of shape changing within the same plane. So we just going, let's say, closer and closer to biological structure. Going not only on the programming of the responsiveness, on the reactivity, we have to programming also the durability for the artificial reef. And here we are applying, so let's say the local feedstock understanding and degradation to better programming the material. So we have made experiments in France, but also in Japan with our colleagues. And we have tried and we have characterized also the revitalization about due to the degradation product of the material. So as I've shown you before, when we immersed the biocomposite within water, there is let's say a biological degradation or leaching, and the purpose is to use this leaching product to allow adhesion of cells within the material and to improve the fouling to go on the material. So this is just ongoing work, and there is a lot of work because this is just a blend between biology, marine biology, technology, and material science also. Now let's move on to solar tracker project. So let's move on to space now. Space have a lot of issue and have a lot of, let's say, common issue with marine application about the severe application. So if we want to develop, let's say, new application of a solar tracker in the space, the environment is very, very, very complex, and we don't want to let's say, to bring astronaut outside to make some maintenance. So we have to propose autonomous system. We have some solar tracker in Earth, but they are based on electromechanical system. So we need to propose something with low maintenance, but also based on in situ material. And this is not so easy because in the moon there is no plant, there is no nothing. There is nothing. So we here propose a new, let's say, or also local feedstock-based shape-changing material, where the actuation is based on just on space environment, on change on temperature on the environment between the day and the night. The local material is based on regolith. Okay, the regolith is the Earth-based bat. So to be honest, even if we are working with European Space Agency, we cannot work on regolith because this is not so common to bring them back from moon. But we can we can use some simulant of regolith, which is basalt. Basalt have a chemical composition which is quite close. The operating range is quite interesting, and this has high toughness, and this is developed as fiber. So we can fiber is quite, let's say, available. And we are using polyamide 12. Why? Because these have been evidenced by our colleague from European Space Agency to be potential polymer that would be used for space application, and that would be potential waste in the future exploration. Let's again apply the top-down approach. Again, the definition of the problem now, if we are applying some application of the space, first would be the thermal strain. There is a lot of application from, let's say, deployable boom. So this is complex for French to say that. In space, but they just realized that the thermal strain was a big drawback because they didn't anticipate the coupling between the thermal variation and the strain induced. So this is the main problem, because also the delta of temperature is close to, let's say, 300 degrees. So let's again look at the biological structure where the humidity, but also the temperature could trigger autonomous motion and should be used as a benefit. So here we are not only, let's say, like the abstraction of the macro scale, let's say bilayer, simple bilayer, because everyone is working on that. But if we just want to have a biological understanding of how the bilayer is working, we need to go deeper and we need to go at the cell scale. Meaning that the layer, let's say the active layer, is made by unitary cells that are, let's say, kind of cylinder made with compliant matrix with embedded very stiff cellulose fiber. And this will trigger, let's say, rotation, and the cooperative rotation will generate the expansion. And this point about the cylinder and the rotation is very important for us, because we have proposed based on let's say a regolith simulant or basalt-based composite. We have proposed two-phase tubular system with active material, which is the polymeric compliance system, and the restraining material, which is the basaltic fiber. Here, so we propose a new concept of, let's say, thermomorph material, thermomorph composite, depending of the vocabulary we want to use. But here we propose, let's say, autonomous rotational shape changing that allows both rotation but also high torque. So this is an example of what is triggered with high temperature. This is the beginning, so this is not a huge rotation. But we have some example that allows, let's say, at least 200 rotation. So what we have done is applying the biological model description, again, at the natural fiber scale, and applying numerical model, very simple numerical model with thermoelastic properties, developing new way of printing with tubular printing, where this is not pneumatic, let's say, actuation, but this is thermal actuation, and characterization of the rotation, but also of the torque, that allow to combine both of these, let's say, paradoxal properties, which allow to have very, very high energy density. Okay, so this was the two examples I wish to present you based on, let's say, local feedstock. I cannot say renewable feedstock because regolith is not renewable. But again, biological structure, or let's say enlarging the potential of biological understanding, is very, very interesting to combine with perhaps, okay, algorithmic and AI, perhaps. But combined with 4D printing allows novel function, which may be very interesting for, again, local feedstock that do not have so much valorization yet. So tomorrow, what would be interesting to work on is to better understanding this biological structure. Of course, I'm not biologist, but I wish to work with biologists again. To work on biological feedstock as smart material, and this is very, very interesting to understand how this material could be used differently if we just change our way of thinking. And the last point, but not the least, is how to control the direction of the actuation. But this is another point. I wish to thank again the founder, the student, of course, And the last slide will be with also Brittany, because I've seen that a lot of people make advertising about their place. So I'm making the same. So Brittany is quite on the west part, so this is very far away from Paris. But this is a good point. And we are very wild, let's say, place with different, very, very nice colors. So we are pleased to welcome you in Brittany if you want to reach us. So thank you very much for your attention, and I open to questions.